let's start. Well, the other classroom that will hear rearrange the tables, so this is still a lecture, so for the people who sent with it back to me, you'll have to look at the screen. Sorry about that, but you can, yeah, you can just like turn around. Who did the readings? Every rose has a thorn. Okay, people, let's start. Let's start. We want to know how to formalize the sentence every rose has a thorn. And how to say every cowboy sings a sad song. Okay, there might be more in logic textbooks. We like to use lyrics from time to time to symbolize English. So this is one example. I had a course where we used "I'm only happy when it rains." What's the next line? I'm only happy when it rains. Do you know the song? If I'm happy, then it's raining, or if it's raining, then I'm happy, right? It's very confusing. We will wait for that. Let's start today's topic. We're moving to first order logic. Now we're putting behind true functional logic, and we're starting to learn a new logic. If you feel this is moving quite fast, then yeah, it is moving quite fast. But don't worry, we will still have opportunities to practice the ideas behind true functional logic also when we move forward. So in a way, we are expanding what you know from true functional logic will be needed and help you to understand what's going on here. We're moving in a way from 0 to 100. That's kind of it's not mentioned in the textbook, but true functional logic is a very weak logic in terms of what it can express. And then first order logic is extremely expressive in terms of what it can say. It might not be obvious immediately, but it's very, very sophisticated logic. So we will, and you can learn it for years, but we will learn kind of the stepping stones, like just the start, okay? But there is like an entire universe behind first order logic. Okay, so it's a very exciting stuff. What do I want to do today? So FOL, this is the abbreviation for first order logic. We'll talk about its building blocks. Then we'll talk about taking English sentences like every rose that is born and moving into symbols of first order logic. And then in the last part, we will talk more about relations in first order logic. Okay? So why is true functional logic very weak? Why did I say that? If you look at an argument like this, Socrates is a human, all humans are mortal, so Socrates is immortal. Are there any logical connector from TFL appearing in these sentences? No, right? There's no not, there's no and, there's no or, there's no if and only if. So there are no true functional logic operators here. So it means that all these sentences have to be represented as atomic sentences, right? We said in true functional logic, if it doesn't have operators, you make it into an atomic sentence, right? So you have H, Socrates is human, M, all humans are mortal, and S, Socrates is mortal. But we're losing a lot of information, right? So now these are just 3 independent atomic sentences. You can write down a truth table. It will have 8 lines. True, true, false, 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 true, right? Every combination of truth and falsity of these things. This is not good because intuitively and according to Aristotle, who gave this example, this is a valid argument, right? You see that if Socrates is human and all humans are mortal, then Socrates also must be mortal. Conclusion, it's impossible for the premises to be true and the conclusion to be false. This means that something is missing from two-functional logic, right? We want a different way to symbolize these type of senses such that we'll be able to think about validity for these more complicated senses. Okay? The way we do it is with these fancy symbols. Basically, we're going to have objects like people and phones and chairs, and we have properties of that objects. So we will have like Socrates as an object and is a human, that's a property. And we want to be able to reason about objects, people, things having certain properties or relations. This is the idea behind first-order logic. Okay? A fun way to say it is that we split the atom, so to speak, when we do that. If this used to be an atomic sentence in two-functional logic, which stands for Socrates is human, now we split it into 2 parts, a property or predicate, and an object or name. So A will stand for Socrates, and H for this property. Okay, we will see that more clearly. Okay, but the point is that we are breaking what we took to be atomic sentences in TFL into smaller components in first-order logic. Okay? A bunch of new symbols, a few familiar symbols we will see in first-order logic. So first we have terms that are either names or variables. Okay, here we said Socrates is human. A was a name for Socrates, and H was for this property being a human. We use for names, we start with A, B, C. This is just convention that everyone follows. And for variables, we will see what that is. We usually start with X, Y, Z. Okay? We don't know yet what it means, but remember there's a distinction between names and variables, and there is this convention. Predicates, these are these properties. We use capital letters to capture predicates. Okay? So these are 2 main things, 2 new main things. Then we have connectives. These are the same connectives that we had in true functional logic. They have the same meaning as in true functional logic. So a conjunction is going to be true if both conjuncts are true. Doesn't matter if you do true functional logic, or first-order logic, or model logic, or whatever, conjunction stays the same. We also have brackets, and we have these very cool symbols that someone typed here. These are exist and for all. Okay? For all x, now we know why the textbook has this funny name. For all x is this symbol. Okay, this is what we are going to figure out. Okay? Not is not a good name for a book, and is not a good name for a book, but for all x, this is another connective, a quantifier. That's a better name. Okay. Any other questions before we dive in? Or any other questions about what we're going to do? Okay, good. Do you take philosophy of language this semester or next semester? You're not taking it this now, right? Okay. So we're starting with a bit of kind of philosophy of language, understanding terms in sentences in languages like English. we distinguish it between a singular term, that is a phrase that refers to a specific entity, and a general term that picks out a kind of entity or a type of entity. So Mira is a name for a dog. It specifies a particular dog, but the word dog is just a general term, right? It doesn't specify a particular dog. Same with Socrates, captures a particular thing in the world, one person, and human or being human, which captures a type of thing, right? Right? Among these singular terms, like Mira and Socrates, people make an extra distinction. We distinguish between what is called as proper names. Proper names pick up a specific entity without describing it. So think about just names, like Socrates. Socrates picks up that person, Socrates, and Michael picks up Michael here. And we compare that to definite descriptions, and these are basically descriptions in English that their job is to pick a particular person. Okay? So Socrates was the teacher of Plato. Plato was the teacher of Aristotle. And one way to describe Socrates is by the definite description, the teacher of Plato. Okay, so the teacher of Plato, that's a definite description. Socrates is a proper name, and they both refer to the same thing in the world. Okay? Likewise, Michael Cohen, that's a proper name. The current teacher of the logic course, that's a definite description, and they both point here, right? By the way, note that we're using the quotation marks because we're mentioning pieces of language, if you remember from 2 weeks. Okay. By the way, we're making the extra assumption that proper names are always picking a particular person going forward. Unfortunately for me, there are many Michael Cohens in the world, including one that was Trump lawyer and sat in prison and all that stuff. So, but we are assuming that there is no ambiguity about proper names. It's kind of like an assumption to simplify things for now. Okay? And likewise with definite description, they aim to pick a particular thing. Sometimes they fail. We will see an example, the present king of France, that's a description. France doesn't have a king, so this description doesn't do much. Okay, we'll get to that later. Okay. In first order logic, we have names that are expressed by these lowercase letters, A to R. We won't have that many names. Think about A, B, C. We can add subscript to have more names. The idea is that ABCs functions like English proper names without any ambiguity. Okay, so they pick exactly one thing in the world. Sometimes you can have two names for the same things. So the same thing. Two FOL names can pick out the same thing, but no name fails to pick up something. There are no empty names. Okay? The idea is that Cicero and Tully, these are the same names for a Roman orator. So two names pick up one thing. It's impossible that one name goes to two different entities. That will be ambiguous. Yeah.
Why is it only A to R?
Because we have a special role for X, Y, Z. So. Okay, we'll see it soon. These are will be used as placeholders. Variables, yeah. Okay, so like in true functional logic, we'll have symbolization keys. In FOL, in first order logic, the symbolization key is more involved. It starts by telling us what these lowercase letters, what objects they refer to. So A is the name of Socrates, M is the name of Mira, M1 can also be the name of Mira. That's okay, right? Two different names refer to the same object, and for name. Okay? Now we get to the XYZ for all X, right? That's the title of our textbook. These are variables. These are harder to understand than names. Don't worry if you don't understand it immediately. And variables, they function a bit like pronouns or placeholders. They give us a way to indicate gaps that we can fill by plugging in names. Okay? That's the idea of a placeholder. I can say X loves Y, but Y doesn't love X. And I'm kind of mean here. What I mean here is that I'm not specifying particular objects. I'm just putting placeholder. X is a placeholder for a name. Y is a placeholder for a name. So X and Y kind of act as placeholders. Okay, for now. Because of that, we don't need to specify what X, Y, Z refer to in a symbolization key. They, in a way, don't refer to anything. And a variable stands for nothing or every entity. It's just like a placeholder. Okay? Questions about this? This is a bit confusing, but as we go along, we'll see. Once you see a full sentence, it makes more sense. Okay? Predicates are part of language that describes properties, right? So I said that first order logic is kind of reasoning about objects and their properties. So predicate is the name we give in the language to particular properties. So is nice, is a human, is in the logic class. These are all predicates or properties of something, right? The idea is that we link up predicates with singular terms to form sentences. Okay, I have the name Socrates, I have the predicate is human, and I can combine them to get a full sentence. Socrates is a human, right? So here we split the atom, so to speak, because we take a sentence like Socrates is a human and we divide it into the name part and the predicate part, or the singular term and the predicate. And again, we use capital letters to describe properties. Whenever you see a capital letter, this means I'm talking about a property. The way we describe or specify predicates in a symbolization key is by giving a description of what the predicate kind of means. And the best way to do it is to, with this like blank space here, to indicate that this is a predicate that can apply to name, right? You need to drop a name for this to make sense. H, B is happy. That's a way to describe what H stands for. Okay? Yeah.
So if you put an X behind the H, is it then like everybody is human?
So HX, just like this, that doesn't make much sense yet. Because X, remember, by itself it's just a placeholder, it doesn't refer to anything before, like when it just stands like this.
So that's incorrect.
That's not something you have to worry about at the moment. Yeah. But it's a good question. Ask yourself, does it make sense at the end of the class? Other questions? Think about if like names are like pronouns, like he, then saying he is happy just without context doesn't make sense. I need to know what he refers to, right? So we need some tool to tell us how to figure out what does it refer to originally. Okay. So now we understand predicates and we understand these singular terms, names. We can start building up first order logic sentences. So here in the red I have a symbolization key. A stands for Socrates, M for Mira, N for Nathan, and then I have the predicates is human, woke up at 3:30 a.m. and is a Terminator. We read HA to be the sentence Socrates is human. And exactly what you asked, HX, X is human, just doesn't make sense by itself. We don't have an English sentence corresponding to We'll never ask you to translate a sentence from English to first order logic, and you will have one of these like dangling axes, or like axes that don't have an interpretation for it. Okay? But names you can have just like a predicate in a name, like TM, Mira woke up at 3:30 a.m. TM and TN, okay, so this is a regular conjunction from true functional logic. Mira and Nathan woke up at 3:30 a.m. Okay? So you can use all the connectives you know from true functional logic to build up sentences. Okay? First the predicate, then the name. In English, in many natural languages, the order, we don't talk like that. We don't say, woke up at 3 a.m., Mira, right? We say Mira woke up at 3 a.m. But that's just like an issue about the word order in English. In first order logic, the decision is kind of arbitrary, but the decision is to first specify the predicate and then the name. Okay, so we kind of read it backwards. Questions? No, okay. Mira woke up at 3:30 a.m. How would you write it down? Capital letter, small letter? TM. Right. Okay. Socrates is a terminator. T1A. Yeah? Nathan and Socrates are human. What is the connective that shows up here? Conjunction. So we'll have a conjunction as a sentence. And we have two conjuncts, which will be HN and HA. Okay, so you can just have a conjunction. You can have a long conjunction for, you all have names, and I can write down a long conjunction.
Does the ordinary method, like if I localize HA and HN, would the method for the sentence to be correct? Do you have to follow the order of the original sentence?
You don't have to follow the order because it's a conjunction, and we know that in conjunction the order doesn't matter. So this is an example of how our understanding, our knowledge of TFL, moves us to first order logic. This sentence will have the same truth value as the sentence did. Because the conjunction is true. In what exact case? They're both true. Right. So the order doesn't. If Mira woke up at 3:30 a.m., then Nathan woke up at 3:30 a.m. Right, this is a conditional. So the main connective here will be the condition. Okay? And then we have two first order logic sentences as the antecedent and the consequent. By the way, as a clarification, in true functional logic, we also had atoms, right? They just look like this. We cannot use them anymore. You cannot write Tm, therefore A, and say, A is an atom from true functional logic. This is not allowed. Okay? So we don't have these like atoms of true functional logic anymore, but we do have all the connectives of true functional logic. Yeah? Okay. Now we move, yeah.
Are we still going to use TFL, or because it seems like FOL is like the more advanced TFL?
Correct. So do you ask whether we use it?
Yeah, are we still going to use TFL? Or what we use?
So the applications of TFL are kind of limited. But it's still possible to look at an argument in English and notice that that the structure of the argument is just based on like conjunctions and negations. Then TFL is enough to kind of like figure out the argument. Okay, like if A then B, A therefore B. TFL explains to us why this is a valid argument. You can build a truth. But it's true that many applications in philosophy and beyond of logic will involve something more sophisticated than two functional logic.
Is the concept of like atomic sentences still applicable? The FOL, like a predicate for the term, is that
Yes.
always has a truth value?
It does, yeah. That's like the simplest thing that has a truth value.
So they will always have a truth value still.
Yeah, like if you have a sentence like this, Mira is a Terminator, then this sentence will have a truth value. But note that the name Mira, it doesn't make sense to say that it has a truth value. But you don't need to know the definition of what exactly is an atomic sentence first of all. Or not. Yeah.
So if you would have TX, that truth value, but also
That's a more complicated question. We will get to it later. Questions? The back?
Yeah, well.
Yeah, well.
Isn't domains isn't working spell?
It's not. Yeah. It's domain. Very good. Okay. We move to domains. No, we move to domains. Okay. To make sense of these x and y's and z's, we need to understand the quantifiers. They go together. This is why you don't have to worry about sense like px. Quantifier is upside down. A stands, like the idea is that it's an upside down A because it stands for all, and the switch E stands for exists. Okay? So we read the expression upside down A variable x as saying for all x. Okay? So this is why you don't have to worry about x's being like dangling by themselves, because they are always connected to a quantifier. Okay, in this case, the universal quantifier. And we say that the variable x is bound or tied to that quantifier. Okay, so the x here is bound to the quantifier here. The y here is bound to the quantifier here. They are tied together, so to speak. Okay? We read that as saying for all x, hx. If h is a human, we're saying for everything, I'm saying everything is a human. For all x, x is a human. Okay? So it's a way to talk, in a way, the variables allow us to make general statements, not about particular names, but about everything. Okay? And the idea is that we can replace the x with every name and get out a true sentence if we start with a true sentence. If it's true that for all x, x is human, it means that a particular object with the name A is human, and B is human, and C is human, and so on. So in a way, the universal quantifier, you can think about it as capturing a big conjunction of names. Right? And this generalizes, this is kind of tricky to see, but this generalizes to more complicated sense. If I have for all y, if there is an x such that t1x, then t1y, I can replace that y here with every name and I will get a true sentence. Okay, so here I'm replacing it with A, here I'm replacing it with B, here I'm replacing it with C. Okay, when I'm saying all of you are enrolled on Canvas, then what is your name? Your name.
I'm George.
Then George is enrolled on Canvas, right? So I can take a universal statement and apply it to every name. That's the idea. The existential quantifier, if the universal quantifier says for all x, the universal quantifier says for some x. And again, we don't care about the number, we just mean there is at least one. And again, the same structure, if you see an x, it must be connected to either universal or existential quantifier. Okay? If I'm saying some of you are from the Netherlands, then it means that either you are from the Netherlands, or you are from the Netherlands, or you are from the Netherlands, right? So when I have a sentence like there is an X, HX, this means that there is at least one name such that will make this sentence true. Okay? There is someone, if I'm saying someone is from the Netherlands, then it means that there is a particular object with a name such that that object is from the Netherlands. Okay? So I can do this replacement to get these sentences. And likewise, if the sentence is more complicated, if the exist y is here and it bounds this variable here, then I can replace this variable with different names and say one of these things is and has this property. So if I'm saying there is one thing on this table which is black, that there is an existent X such that X is black. This will be true for, let's call my phone, Phony the phone. Okay, so this is Phony the phone, that's the name of my phone. Phony the phone is black. Questions? Okay. How would you write down everyone is human? So there's an HX, okay, but then there's something missing.
Yeah, so it's an upside down AX and then between brackets HX.
And that we read this for all X, or every X, and or universal quantifier X, yeah. Okay. Don't worry about the conventions for the brackets yet. Okay, we haven't reached that. But here we don't use the brackets. Someone is human. How would you write that down? That would look similar.
Basically, same with them with the exists.
There exists an X such that that X is a human. Okay. So in a way, whenever you have an X, a Y, it's always about a someone or about everyone. This is what we mean by being like a placeholder. There is a human, and Mira woke up at 3:30 a.m.
So do you need to use the brackets at the first two or not?
No, for now.
Okay.
There is a human, and Mira woke up at 3:30 a.m. What is the main connective here? A conjunction, right? Okay. It's a conjunction where one conjunct is just the same sentence. There is a human, and Mira woke up at 3:30 a.m. Why J? That's a mistake. Okay. Should be M. If Socrates is a terminator, then everyone is. This is a more complicated idea. But first of all, when we look at the sentence, what is the main connective that shows up here?
Conditional.
Conditional. And then when you say a word like everyone, now what will it be? For all, right? So if Socrates is a terminator, then for all X, X is a terminator. Then everyone is a terminator. Okay? Because this is a more expressive language, logically speaking, there will be more ways to take English into first order logic. Okay, so then everyone is, or then for everyone, it's the case that they are the terminator, right? There are different ways of saying it. Okay? If someone is a terminator, then everyone is. Okay, now it's still a conditional, right? But both parts of the conditional involve quantifiers. someone, what does it stand for? The existential, everyone for the universal. Okay, so we can write it down like this. If there's an x such that that x is a terminator, then for all x, and x is a terminator. Note that these variables are in a way it's the same x, but in each part the x is bounded by a different quantifier. So they kind of mean different things. You always need to ask yourself, when you see an x, a y, or a z, what does it bound? What quantifier does it bound to? Okay. So here it's bound to the universal, and here it's bound to the existential quantifiers. Okay. This means something else. Okay. You can also, fortunately or unfortunately, depending on your views about first order logic, you can have the x here in a different, for all x in a different position. But this has a problem because look here, we have an x, and it's not clear whether it's connected to this quantifier or to this quantifier. So this is a bit confusing, and we try to avoid this. Yeah.
Why is that unclear?
We just strive for full clarity in the sense that for every x, it's always completely clear. Does it refer to which quantifier does it refer to? Okay, here I have two options, right? Because this bounds in x, the universal quantifier, and the existential quantifier bounds in x. Okay, I don't want to be in this situation. How do I avoid? I just use a different variable. I can use a y, for example. Okay. So the way the textbook says it is that a single variable cannot serve two masters simultaneously. There is always, for every x, there should be exactly one quantifier, existential or universal, that kind of like specifies it. Okay? And another way to say it is that if we want to replace the x with a name, we don't know if we should do the replacement according to the universal or the existential quantifier. As I said, we can avoid this by using just a different variable. Now, the y here is bounded to this universal quantifier, and the x here is bounded to this existential quantifier. Yeah.
So, if we follow this rule, would we also have to change it in the first example on the slide?
So this, yeah, that's a very, very good point. We don't have to because the x here is directly connected to here, and the x here is directly connected to here. So there is no situation. Remember, we had this issue about the scope of a negation, like how long does the negation go? We also have it for the scope of variables. So I can draw it. If I have a sentence for all y, x, y, t1, x, therefore t1, y, the scope of this y is everything here. Okay? The scope of this x is only this part. So we're not, and at the top there is no clash of scopes for the x. Right? They have like a small scope within the antecedent and the concept. Okay, so again, like with negations, with other two-functional logic scope, it's good to kind of draw to yourself what is the scope of each quantifier, the universal and the existential. Okay, because it gets pretty confusing. Yeah.
Do we have to use some x instead of y relatively clear those for the scope to be?
So if we have this, then I'm asking what is this connected to? And I see that it's inside two scopes, and both of these scopes try to specify the scope of x. They both refer to an x, and I don't want to do this. So I'm kind of like asking, is this x connected to this quantifier, or is this x connected to this? We don't want to. That just makes things confusing and harder. Okay. We need domains, not domains. We need domains to understand what's going on. If I say all the beer is gone, I can mean all the beer in the universe, in the Milky Way galaxy, in Tilburg, in my apartment, in my fridge, right? When we say a universal statement, we need to know who are all these things that we're talking about. Okay? In English, we use context to figure out what is the scope, like what is how general I'm speaking and I'm talking about, right? And it's obvious that I'm not talking about all the beer in the world is gone. And when I'm talking to a friend about like, when we are at my home or something. In first order logic, we don't have this context tool to disambiguate statements. And we just need to explicitly say what are all the things that we consider in every situation. Okay, this is called the domain. The domain is all the things that we're talking about in a particular situation. So this is another thing that comes up in the symbolization key that you give for an FOL sentence. You need to say what is the domain. So you can say the domain is things in the fridge. Or you can say the domain is physical objects. Or you can say the domain is everything or universal. Completely everything. But it's important to specify the domain because it might affect the meaning of the term. Okay, so remember the symbolization key now has to specify the names, predicates, and what is the domain that we're talking about. Quantifiers get their interpretation from the domain, right? Now, when I specify a domain and I say for all x, what I actually mean is for all things x in the domain, in the fridge, for example. Or there exists a thing x in the fridge such that. Okay, so another way to think about it is when we talk about all things or exist a thing, it's always relative to the domain specified in the symbolization. Yeah. To assess the domain, what do you mean? You don't have to like explicitly write down this object, and this object. So just like all people, all animals, all things on planet Earth, these are all like acceptable domains for this class. Okay. There are a few restrictions on domains. The domain must always include at least one thing, so we don't have empty domains for now. And each name picks exactly one thing in the domain. So this is another way to say what I said before. And together with these two things, we can jump from a statement like Nathan is a terminator to the conclusion there is something which is the terminator, right? And we want to be able to make these connections. So a domain must have at least one member, and a name must pick out exactly one member of the domain, but a member of the domain might be picked up by one, many, or no names. So it's still possible that we have something in a domain that doesn't have a name. But if something has a name, then it has a particular name. Yeah.
If you use a domain, dog's name is Mira.
Yeah.
You cannot use the name Mira anymore.
Right. That's you're violating the rule that our names are completely unambiguous. So you have to do like Mira 1, Mira 2, Mira 3. That will be one way to like make it unambiguous. But you're right that it's a way to pick a domain. It's a way to pick a set of objects. Yeah. Other questions? Yeah.
Where do you write down?
So the symbolization key, maybe there's a next. Yeah, you just like. Yeah. When you specify the symbolization key, you want to have to say somewhere what is the domain. Okay. Okay, let's take a 10-minute break and let's come back to 11:40. Singular general. Reptile is there. General. It's not English. This tells you when you predicate that if you as the anything includes that, then it will always be a name. And reptile is going to be a reptile. This is the first thing you need to notice about the strict logical structure. One in one, general group.
They would know my name.
So this kind of indicates this part of the numbers that I would have to one. But here, say for all x, that x is elevator and that. Here again, because we're still talking about the same thing, so we want to kind of keep the same scope, the same quantity. Yeah, although the word any, the word any is this is what it means, right? Like other words, yeah, no, it's like general to any sound. But the important thing is to realize that here, talking about just same thing, right? Also picking something up and then saying things also. And what is the reason for doing this sentence? What are the real meanings of this sentence you don't have to? So this is how we can know from you. They have the same meaning. So in a way, we will never deduct but they are logical. Yeah, and it's all so Bob is either fine or satisfied. Negation. You can have negation, conjunction. Same for FOL. Yeah, but now you need to, this is why reason, this stage you start to realize already like what are you here. Don't give the logical equivalent. But don't give how many there are sometimes many ways, yeah, there are many ways of giving the same sentence. But I agree that sometimes there are two jumps, like very salient ones, and then it's not still possible to do right away. But I will start. I have promises to keep and miles to go before I sleep. Do you know this? of promises to keep, a lot of things to do today, so I want to start. But you know the poem? The woods are lovely, dark and deep, but I have promises to keep and miles to go before I sleep. Okay, let's go back to first order logic. Okay, now people, I have promises to keep. Okay, let's come back. The goal of first order logic is names, predicates, quantifiers, and connectors. Okay, so we covered all the elements of first order logic. As I said, it takes years to realize what it means, but we're there. We're on our way. Symbolizing more complicated sentences is simply a matter of combining these elements in the appropriate manners. Many times it's good to do it in steps. So when we do this English symbolization of first order logic, it's important to understand the structure of the English sentences. And as I said, like sometimes you can do it directly, sometimes it helps to paraphrase. If you notice, like I keep saying, wow, English is more complicated than it seems. English has this ambiguity, English has that ambiguity. That's kind of like gives you a glimpse of what people do in philosophy of language and linguistics. So like realizing how things are complicated once you start trying to like, theorize them. Okay, so that's a cool stuff in general. Linguistics is cool. But we're in logic. Okay, there's this phenomenon of, who wants to pronounce this together with me? Syntagmatic adjectives. We said it once and we're done. Okay? I'm not going to say it again. Let's say I have the sentence, Steve is a happy American. Only once. Let's say the predicate F is happy and A is American, S is Steve, the domain, all humans, let's say. How would you formalize this? This is actually a conjunction. I'm saying Steve has two properties, being an American and being happy. Okay, that's a bit tricky because the conjunction doesn't show up. But I have two adjectives, so I say, I'm conjoining two adjectives. Very nice, but it doesn't always work. Zlatan is a good footballer, and Zlatan is a person, and Zlatan is a good person. How would you formalize these? So G for is good, F for is a footballer, and P for is a person. A is Zlatan. So Zlatan is a good footballer, maybe the same idea. GA, Zlatan is good, and Zlatan is a footballer. Zlatan is a person, PA, and Zlatan is a good person, GA and PA. Okay, there's a problem here. Yeah.
I was going to ask about the problem.
Okay, Zlatan apparently is not necessarily a good person, even though he's a good footballer. Okay. That's what the slides imply. When you say Zlatan is a good person and you use, and the way you formalize it is by conjoining two adjectives, you might lose the real meaning of what we care about. Okay? There's a difference between being a good footballer and between being a good person. It does not always mean that you're good and you're a footballer, and you're good and you're a person. In a way, the good is connected to the footballer or to the person. They cannot be separated. So the correct way to symbolize it is to have the predicate for a good person and the predicate for a good footballer, and then not accept these, but to replace it with different predicates. Okay? The way to remember it is when you see two adjectives in a row, you need to carefully assess whether they are treated as the same conjunction, as a conjunction or not. Okay? A black bear is black and a bear. A polar bear lives in the polar region and is a bear, but a teddy bear is not a bear. Okay? So in languages make tricks on us. Okay? That's actually, there is a famous incident in the history of philosophy where Immanuel Kant gave a theory. He called it transcendental idealism. And people said, you just come up with more idealism. And then he said, no, transcendental idealism is not idealism. Same idea here, right? Being a good footballer does not imply that you're good always. Again, tricks that natural language do on us and we don't even realize. Okay. Every dog in the house is a Jack Russell Terrier. Some dog in the house is a Jack Russell Terrier. Not all dogs in the house are Jack Russell Terriers. No dog in the house are Jack Russell Terriers. What is new in these senses? We have quantifiers. We don't have names here, but we also have another thing in 3 and 4. Quantifier and negations, okay? Quantifiers and negations, they can work together, and it's not always straightforward to see the connection. Every dog in the house is a Jack Russell Terrier that doesn't have a negation. You might say for all x, hx, and jx, but this is in red indicating this is wrong. Okay? Why? Because it implies that all the dogs in the world are in the house. And this is not what we want to say.
Yes, in the house, you're not a domain.
So no, I specified the domain is all dogs. So it can be dogs in China and in America, but my house is in Tilburg. Okay, so although it's tempting to think about it like this, that would be wrong. The way we actually think about this English sentence is saying, the red sentence, every dog is both in the house and a Jack Terrier. This is not what we mean, right? Not all dogs, fortunately, are in my house. The way we say it is, for all x, if x is in the house, then x is a Jack Russell Terrier. So actually, this sentence is a conditional. That's confusing because we don't see the conditional, but that's kind of the power of first order logic to kind of combine the universal and the conditional to get sentences like this. Yeah.
Why can you not use the domain all dogs in the house?
You can, but then it will change your the way you're thinking about it. If all the dogs in the house, then you can just say for all x, jx, right? But here we want to talk about other dogs as well, not only the dogs in the house. Okay, so the way to remember it is that many times universal quantifiers come with an implicit conditional inside them. Okay, so every f is a g is symbolized for all x. If x is an f, then x is a g. And remember, I'm using the fancy font here to indicate that it's kind of like a placeholder for any predicate that you want. Okay, every f is a g is presented with a universal quantifier and a conditional. Some dog in the house is a Jack Russell Terrier. What do you think? Is it a conjunction, a conditional? There is an existential quantifier here, right? But what is the extra structure inside the existential quantifier? Okay, you might think there is an x such that if x is in the house, then it is a Jack Russell Terrier, but that's confusingly enough would not be the right answer. Why is that? Remember that the conditional can be true if the antecedent is false, right? So another way to say it, some dog is such that if it is in the house, then it is a Jack Russell Terrier. Note that every conditional is basically saying, if you remember the truth table, either A is false or B is true. This is what the conditional is actually saying. Now you can see it using the truth tables. So I'm saying there is an x such that either x is not in the house or it's a Jack Russell Terrier, and this is true if there are no dogs inside the house, and this is not what we mean. Yeah. To the universal, yeah. Okay, so how would you do it? You actually do use a conjunction here. You say there is some dog that is both in the house and is a Jack Russell Terrier. Okay? You say there is something such that that thing is in the house and it's a Jack Russell. This implies that there is something in the house, which is kind of what we want when we say there is some dog that is a Jack Russell Terrier in the house. Okay? So the way to remember this, sum f in G is formalized as there is an x such that x is an f and x is a g. Okay? We're kind of covering, of course, English has infinitely many sentence patterns, but we cover ones that are kind of common. So for all x is a g or some f is a g. Now we add negation to the story and it gets complicated. Not all the dogs in the house are Jack Russell Terriers. I'm negating something. What am I negating? If you want to remove the negation from the sentence, how would it look like? How would you say it in English if you remove the negation? Right. You say all the dogs are Russell Terriers, and then you negate that. Okay. So what you're doing is you're negating a universal quantifier. It's not the case that every dog in the house is a Jack Russell Terrier. I'm negating an entire universal sentence. So I can do it like this, right? I symbolize it the same way I did as before, and then I add a negation in the front, right? It's not true that for all x, if x is in the house, then x is a Jack Russell Terrier. Okay, there's another way to say not all the dogs in the house are Jack Russell Terriers. How can that be true? Maybe I have a Labrador in the house, right? Maybe I own a Labrador. Maybe I own a Poodle. I don't know, right? I don't, but maybe. If that would be the case, then not all the dogs in the house are Jack Russell Terriers. So you can say there is a dog in the house that is not a Jack Russell Terrier. It will have the same meaning, right? And this can be represented with an existential quantifier. So these two senses are logically equivalent. There is an x such that x is in the house and x is not a Jack Russell. These two senses are both fine and acceptable ways of representing not all f's are g's. Okay? So both of these are okay. Now the hardest part, no dogs in the house are Jack Russell Terriers. So I'm negating something, right? It is not the case that there is some dog in the house that is a Jack Russell Terrier. I'm basically negating the claim that there are dogs in the house that are Jack Russell Terriers. So I'm negating an existential statement. So this is one way to do it. Negation, existential quantifier x. X is h and x is j. X. But note that there's another way to say it in English. No dogs in the house are Jack Russell Terriers. Another way to say it is that every dog in the house is not a Jack Russell Terrier. So actually, this is also a universal statement. And you can say it like this. For all x, for any dog, if that dog is in the house, then it's not a Jack Russell Terrier. Okay? This has the same meaning as no dogs in the house are Jack Russell Terriers. And again, both of these ways are good ways to formalize no f's are g's. Okay, so to summarize it, if you have a sentence like not all f's are g's, there are two ways to write it down. They are both equivalent. For all, this should have a negation here. That's a big mistake. There should be a negation here. Sorry about that. It's not true that for all x, if x is an f, then x is a g, or there is an x such that x is an f and it's not a g. And the sentence no f's are g's, again, there are these two ways of symbolizing it. Both make sense. Whatever makes more sense to you, remember that, and then remember it's equivalent to the other. Basically, we see that there is an interaction between the quantifiers and the negations. When you have a quantifier and negation, you can kind of like, depending on the order you put things, you can use both of them. Okay? Confusing. So for now, just remember that there are these logical equivalences. And now logical equivalents mean that they mean exactly the same thing. They are true exactly at the same times. For all x not x is logically equivalent to it's not true that there is an x which is an ax. Okay? There is an x not x is logically equivalent to saying it's not true that all x are ax. Okay, so just note how you basically put the negation in a different place and then you switch from a universal to a existential statement. And we've just seen the example of it's not true that for all x, if x is a f, then x is a g is logically equivalent to saying that there is an x which is an f, but it's not a g. Okay? And likewise, it's not true that there is someone who is both an x and a g is logically equivalent to saying that for everything, if that thing is an f, then it's not going to be a g. Okay? For now, try to remember them, and as we go along, they will actually make sense. Okay? And if A is like an alien for Mars, then I'm saying for everyone in this class, it's not true that you are an alien for Mars, and this is equivalent to saying it's not true that there is someone here who is an alien from Mars, right? So, same idea can be represented as a universal or an existential. Yeah.
Could you just do the last one again? The bottom one? Yeah. What is that saying?
So let's look at the example of the no dogs in the house are Jack Russell Terriers. Okay? So I'm saying that if there is any dog in the house, that dog is not going to be a Jack Russell Terrier. For any dog that's in the house, it's not going to be a Jack Russell. But I can also say I'm negating the claim that there is something in the house which is a Jack Russell. Okay. Okay, we'll talk more about quantifier scope. I started to talk about it. It's a very important notion. Okay. We said that names must pick up exactly one thing in the domain, but I didn't say anything about predicates yet. Predicates can fail to apply to anything in the domain. So I gave you just now the example of is an alien from Mars. This is a predicate, but it actually doesn't apply on anyone here, right? So it can be empty, so to speak. And yeah, it's called an empty predicate. Okay, so there are no Pokemons in real life. So is a Pokemon is an empty predicate. It doesn't apply to anything in the real world. How would you write all Pokemon are cute in first order language? What word here is kind of like red alert? This is first order logic. Again, all, right? All, that's the universal quantifier. For all x, if x is a Pokemon, then x is cute. Okay? Some Pokemon are cute, some, what will it be? How would you write it down? Existential. You can also say it out loud. So there exists an x such that x is a Pokemon and x is cute. Now, let's take for granted that there are no Pokemons among people. In the domain of people, there are no Pokemons, right? Which of these two sentences is true? Is sentence 6 that says there is something which is a Pokemon and cute. Is that true? No. So we agree that sentence 6 is false. Sentence 5 is the confusing one. Okay? Sentence 5, you can think about it as asking you to do something. It tells you, find me something in the domain, and then see if it satisfies the antecedent and check whether it satisfies the consequent. The problem is that I cannot find anything in the domain that satisfies the antecedent. Right? I'm looking all over the domain of people, and there's no Pokemon. That's in the situation of an empty domain, right? For this reason, we treat F5 to be true. Okay? It's the same idea with validity, same idea with the conditional. If we fail to satisfy kind of like the conditional requirement, then we say that the thing is true. The same way that when we fail to, when all the premises are always false, for example, then we failed to show invalidity, so we call it invalid. Okay, when a premise has a contradiction, then it's always, the argument is always valid. And when the antecedent in a predicate is empty, then the sentence is true. It has the name of being vacuously true. Vacuously with the idea that the predicate is empty. Okay, so in first order logic, the sentence all Pokemon are cute is true because there are no Pokemon. It also means that the sentence all Pokemon are ugly is true because, again, for the same reason, there are no Pokemon. A bit of confusing, but that's not the first confusion you had in this class. So, okay. Let's do some examples of the interaction between the conditional and the universal quantifier. If Marco is a footballer, then he is handsome. Note that the word he here refers to Marco, right? We understand that. So we can say it also as, if Marco is a footballer, then Marco is handsome. Does this involve any quantifiers? No, right? These are just combining atomic sentences. Right? This is confusing because you might think, the word he is a pronoun, so there must be a variable, a quantifier, but there is no quantifier. Compare that to, if any person is a footballer, then they are handsome. What does they refer to in English here in this sentence? To that person you picked, right? To that footballer. So how would you write that? This does require a quantifier. Okay? I'm saying whatever person I pick, if that person is a footballer, then that person is handsome. For all x, if x is f, then x is h. Okay? So in English, these two sentences are very similar. They have a very similar consequent, but in the logic, they look very different. Okay? That's kind of something to remember. If anyone is a footballer, then Marco is handsome. Anyone, any, it's kind of like in English, it's a very confusing word once you start learning logic. So any, you see any kind of like, take a moment to think. If anyone is a footballer, then Marco is handsome. What does it say? If there is one footballer, then Marco is handsome. Actually, there is no connection between the antecedent and the consequent. So how would you write it down? If there is one footballer, how would you write this part of the sentence? What is the quantifier that plays a role here? The existential, right? I'm saying there exists a footballer, and then I'm putting that as an antecedent of a conditional. If it's true that there exists something which is a footballer, and then the consequent has nothing to do with the quantifier anymore, right? The sentence, Marco is handsome, is something that does not require a quantification. If anyone is a footballer, then they are handsome, okay? English is like confusing. One way to understand this sentence is, if any person is a footballer, then that person is handsome. How would you write this down? If you're confused. Good, I'm also kind of confused. You write down like this. For all x, if x is a footballer, then x is handsome. Okay, so English is a bit confusing because we started in both cases with if anyone is a footballer. This is just a highlight that the word anyone in English is a bit confusing.
So the first one is vacuously true.
Here, no, this one, in a world where there are people, and the domain is people, then there is someone
Okay.
who is a football.
But even though the consequent has no relation.
Right, the consequence is just unrelated. Okay.
So it's just true.
Yeah, it's just true. Yeah. The second one is not true, or depending on your view about football and being handsome. But the important thing is that the English any, the word any, is kind of confusing. Reminder: this is not a course in English. This is a course in logic. So the important thing is to understand the logic. And here. Okay. Let's move on to more complications. First of all, we haven't seen multiple quantifiers in one sentence applied to each other. We'll see that. And we've only seen predicates which are property. Is nice, is American, is handsome, describing a property. But logic, first order logic allows us to describe relations between objects as well. Okay, taller than. Okay, here are the examples. We call a one-place predicate and predicates that only take one thing. Okay, we call them also properties. Two-place predicates are things that will take two names, two singular terms to make sense, right? So loves is like love, right? You need two things to make the sentence meaningful. So we call it a relationship or relation. Is adjunct to, is taller than, is funnier than, is greener than. These are all relations. You can also have three-place predicates. Is between and Okay, this is a relation that takes three singular terms to make sense. Okay, you can have 4, 5. Don't worry, we will stick to 1 and 2 most of the time. Okay, but 3 from time to time. Okay, but the idea is that relations can have multiple placeholders, so to speak. Okay, and the order is important when you have two places in a two-place predicate. So let's have the domain of all people, and let's have Finn and Prince of Bubblegum be our famous objects here, and we have this relation L, loves Okay, so the ordering matters, right? Finn loves Princess Bubblegum is going to be L, F, B. Okay, Finn is the first position, Bubblegum second position. Finn loves Finn. Nothing wrong with loving yourself. You just put the same name twice, right? So F loves F. Okay, these are two different senses, right? They use the same predicate, same relations, but they mean something else. Finn loves Princess Bubblegum, but Bubblegum does not love Finn. Okay, what is the main connective? Conjunction. Okay. Finn loves Princess Bubblegum, that's the same as the first one, LFB, and it's not true that LBF. Okay. The only thing that changes in the conjuncts is the ordering, right? But the ordering matters. Princess Bubblegum is loved by Finn. How would you write that down? What comes first, F or B? F. Okay, it's LFP because it has the same meaning as Finn loves Princess Bubble. Okay? Another way to say it is that a relationship like to love is not symmetric. One person can love another person, but that person does not love them back. This is not only true for love, it's also true for many other relationships. So some relationships are symmetric in that sense, some are not. Is taller than is also not a symmetric relation. Okay, and then when these things are not symmetric, the order matters. Okay? Aha, that's the fun, now we're getting to like really using first order logic. When we say everybody loves somebody. Okay? Also a lot of songs here too. Think about the songs, right? When we write the logic text. Everybody hurts. And what does it mean? It's a bit ambiguous. We have two quantifiers. We can say for every person there is some person that they love. Or maybe there is some particular person that every person loves. Doesn't really matter how you interpret it in English. What's important for us logicians is that there are two ways, and there are ordering of the quantifiers here is different, and then we get two different sentences. Okay. What is the first quantifier in the first sentence? Is it universal or existential? Right, it has like universal and then existential, versus the second one starts with an existential and then moves to a universal. Okay? If we stay with the same relation, the first one will be for all x, there is a y such that x loves y. Everybody loves somebody. Okay? This is true in the love triangle. Ron loves Hermione, but not Harry. Harry loves Ron, but not. So you can think about it like this. This is a love triangle, right? It's true here that anyone you pick loves someone. It's not true that there is one person that everybody loves, right? That will be the second sentence. There is someone such that all other people love that someone. Okay? In order for this to work, everybody needs to love one particular thing or character, including that character himself. Harry has to love Harry in order for this sentence to work. Okay? The power of first order logic, in a way, comes from the way we can use multiple quantifiers. It can get very, very sophisticated and complicated once you have many quantifiers kind of like stacked on top of each other. Yep.
Is the second one wrong?
What do you mean? In the Harry Potter, I don't know. Yeah. No, what do you mean? Like, so it's false in a love triangle. Okay? In a love triangle, the first one is true and the second one is false. Okay? And why is this false? This says that there is someone such that everyone loves that person. Okay? Does everyone eat? Let's do A, B, C, okay? A loves B, B loves C, and C loves A. Okay? Do you see? Does B loves A? No, right? So it's not true that everybody loves A. You can go, does C loves B? No, right? C loves A. Does A love C? No. And A loves B. So there is no particular person in this love triangle in which everyone loves. Okay? How would it look like? You can have, you can have something like this. And now imagine the arrow again represents the relations of loving. So B loves A, C loves A, and also A loves A. That will be, there is one particular thing, person A, such that everybody loves A. Everybody loves brains. Yes.
For the first sentence, it could also be true if A and C both love B, and B loves one of them, right?
Right, yeah.
Because otherwise the sentence would have to be for every person, there is some person that loves them.
Right, it doesn't, you're right. This is it doesn't capture, love triangle is one example, but there are other examples that capture. Graphs of love, that's what we're doing now. Another example is everyone has a mother, right? For every person you pick, that person has a different person, that person is their mother. But it's not true that there is one mother shared by everyone. These are two different sentences. This is a famous confusion in the history of humanity. The fact that the order of quantifiers matter. For all x there is a y is different than there is an x for all y. If you're a fancy logician, you could kind of abbreviate the order of the quantifiers in the brackets here. People often confuse this ordering, and it's so often that there is a name for it. It's called a quantifier shift fallacy. When people make a mistake, okay? And you know, like ancient, there's this all these like ancient civilization conspiracy theory stuff, and all that stuff. It can be true that for every civilization there was a flood that destroyed that civilization. That's different than saying that there was one flood that destroyed all civilizations. Okay, that's another example that does not involve being a mother or loving each other. Okay, this actually comes up quite often. This is not a course about fallacies, but it's a good thing to know that this confusion comes up pretty often. So remember, the order of the quantifiers is very, very important. And we are done. I managed to finish everything. What we'll do next time, we'll talk more about first-order logic. We'll talk about extra things you can put in first-order logic. Please read the rest of the chapters, 77 and 91. And in the tutorial this week, we'll start doing first-order logic formalizations. Okay, so we're moving away from true functional logic. I'll stay here if anyone has more questions.